So what we know so far in organic chemistry is there are tens of millions of known organic compounds, and more are being isolated and synthesized and identified every year. Now, fortunately, the chemical behavior of every compound is not entirely unique, and instead, certain relationships among molecule structures gives us an idea about how similar they are, or how different they are, and how similar and different the molecules can behave. So, for example, as we learned in chapter 1, molecules having the same functional group tend to react similarly. Here in chapter 4 and later in chapter 5, we develop a broader understanding of how molecules are related, and we are going to delve into the consequences of these relationships. One of the ways that molecules can be related is by mirror images. And this is a Norman Rockwell painting. And the reason I chose it is because, of course, there's a young girl looking in the mirror. And we're going to start talking about some mirror images of molecules. So let's start talking about how different molecules can be related. So what we're going to focus on is we are going to examine the relationship among isomers. And these isomers are distinct molecules that have the same chemical formulas. And so I've got written here for you, two molecules are isomers of each other if they have the same molecular formula but are different in some way. Now, there are a variety of different isomers that we can see here. So I really love this flowchart. It's going to come up all through chapter 4 and 5, where you have the same molecular formula, but these molecules are different in some way. So we're comparing two molecules and they're different in some way. So these would be isomers. And then if they have the same connectivity, then they're stereoisomers. If they don't, then they're constitutional isomers. And then if they're different by rotations around single bonds only, they're conformers, right? If they're not, then they're configurational isomers, and then we'll get down into mirror images. Now, the things that we're going to focus on in this particular chapter are constitutional isomers, which are shown here in red, and conformers, which are also shown here in red. Configurational isomers, which includes diastereomers and enantiomers, are going to be discussed in chapter 5. So we will use this flow chart all the way through. Now, these differences in isomers and the way they're different give rise to different types of isomerism. So these differences give rise to different types of isomerism. Okay, so let's go ahead and dive into conformers, and then we will hit constitutional isomers in a little bit. Okay, so if there was a jump there, it's if you see a jump between slide 3 and 4, it's because I advanced too much. You didn't miss anything, but I did advance, so it might break up just a hair there. All right, so let's talk about conformers. A pair of conformers a lot of times are called conformational isomers. So those are just synonyms for each other. And these guys are going to differ only by rotation around the single bond. Okay. Now, these conformers cannot be isolated from each other. So I'm going to okay. To more easily study conformers, it's helpful to have a systematic way of depicting molecules having different angles of rotation around single bonds. And so that is rotational conformations, which we're going to talk about on the next slide. Now, these conformers are stereoisomers of each other. So we can think of stereoisomers as a large umbrella term, right? So there's the stereoisomers, and here conformers fall under that term. So, but understand, configurational isomers, conformers, diastereomers, and enantiomers are all types of stereoisomers, right? So this is like a big umbrella, and these all fall underneath it. Now, conformers are going to have the same connectivity, right? Meaning that the same atoms in both species are bonded together by the same types of bonds. So let's talk about what this looks like. Okay, so again, if there was a jump there, I advanced too far. And so if it broke up, you didn't really miss anything. So we're going to go ahead and get started. So when we talk about rotational conformations, it's really hard to imagine unless you build the molecules. This is why we are going to build the molecules in lab and in class, and we'll talk about that. Now, I want to point something out. There is also going to be an additional video where the molecules are built for you, and so you can watch that as well. So what we're talking about here with the rotation is I want you to look at this carbon. Do you see how this X is up? Well, if you can imagine this X, which is just another atom, and this X are down, and it kind of forms a tripod here, okay? But I want you to notice only one is down and these two are up. This can twist where only one can be up and two can be down. So that's what we're talking about as far as different conformations that you could have with rotation. So it can change the way it looks. One of the ways to illustrate rotational conformations is with Newman projections. And so Newman projections offer a convenient way to illustrate rotational conformations. A Newman projection is just this two-dimensional representation that we're shown here. This is a Newman projection. And it's viewed down the bond of interest. And so what we mean here is look at how this is color-coded. This is red and this is black. And so this dot here in the middle corresponds to this carbon. And then this big circle in the back corresponds to the carbon shown here in black. So the dot here in red is this carbon, and the large circle in back right here is that's shown in black is that carbon right there. And so we're viewing it, if we were to come here, and I'm going to draw a really creepy eye. Maybe it's not going to, I'll put some eyelashes on it so it's not so creepy. Oh, here, we'll do an eyeball there. Okay, so if I'm viewing it right down, this bond right here, that's what we see. So we have a front carbon and a back carbon. So let me put some words to that. So the two atoms directly connected by the bond of interest are shown explicitly. Okay, and when we talk about this, them being shown explicitly, the near atom is depicted as a point, right? And the more distant atom is depicted as a circle. Okay, so that means the nearer atom to us is the one that's shown in red. That's that point, that's the front carbon. And then the more distant atom is that larger circle. Now, bonds to the front, right, are going to converge to this point. So these three things, the Y here and the Y here, these two Y's here are shown up like this, and this Y is down. And then these two X's here are shown down, and that X is up. So bonds to the front, atom converge at the point. Whereas bonds to the back atom connect to the circle. Now, let's then look at rotations. So each angle of rotation that we see defines a particular dihedral angle. And so when we talk about the dihedral angle here, this corresponds to the angle between the CX on that generic molecule and the CY bonds. And so what we're looking at here is this Y and this X. And so we are going to keep the Y stationary and we're going to rotate the X. And so if we rotate just over one time, right, then what you're going to see here is this relationship is 60 degrees. If we rotate over two times, it's going to be 120. If they're opposite, 180. They're 240, 300, and then 360, and we're back where we began, okay? So there's the Newman projection. If you look and view down that carbon-carbon bond, right, there's your Y and there's your X. So there's your Y and there's your X. They're color-coded. The Y is still in front, and there's the X. And then the Y, and then the X. And now they're opposite sides of each other. And this is what corresponds to what we're looking at here, okay? This is from the side. And so when I was talking before and I said, hey, look, these two things kind of form a tripod here, and this is pointing up, that's what you can see there. And so you can see how these align. So when they sit on your desk, they're going to sit really nicely because they align there. So I want us to look at an example problem. So the example problem is to draw the Lewis structure of the molecule with the following Newman projection. And so when we look at this, so if there's a jump there, I just had to pause it for a second. So if we look at this, we need to ask ourselves these questions. Which atoms are connected by a bond not observed in the Newman projection? And then what atoms or groups are attached to each of those atoms? So what we're trying to do here is go from this Newman projection into a molecular formula, a Fisher projection, okay? So when we look, the bond that's not shown is a carbon-carbon single bond, okay? And so I know at the dot in the middle, there is a carbon, right? And so that's going to be my front carbon. And then I know that that big circle in the back is another carbon. And so that's my back carbon. And so that's where I'm going to start first, okay? Now, I'm going to look at just the front carbon, and I'm going to color code this in green so that we can see it, okay? So that front carbon I'm going to show in green there. And so now I have to look and say, what's attached to that front carbon? Okay. Well, when I look at the front carbon, it's bonded to 2 hydrogens and a CH3. So I'm going to come over here, I'm going to say, great, we got a hydrogen here, and a CH3 here. Okay. Then I'm going to look at this back carbon, right, which I'm going to show here. Let's do it in blue. Whee! Okay. And so it's right here. And I'm going to see what's attached to that. And when I look at what's attached to that back carbon, I see there are 3 hydrogens. So 1, 2, 3. Okay. And so that's my Lewis structure. If I were to draw that as a condensed formula, right, it'd be CH3, CH2, CH3. So this is a Lewis structure of just propane. And what we're doing, again, if I were to correspond those bonds to that, is there's that back carbon that's in blue. And then here is the next carbon, which is in green. And we're looking down those 2 bonds, right? And that's why CH3 is down. So I'm hoping that helps you see how we go from a Newman projection to a Lewis structure and then to a condensed structure. Now, to better understand the nature of rotation about a given bond, we can perform something called conformational analysis. Now, when we look at conformational analysis, it's just a plot of the molecule's energy. Okay, so here is the relative energy on the y-axis, and the bond's dihedral angle here on the x-axis. So again, that dihedral angle, we're going to look between these 2 hydrogens that are shown in red. And so that's the hydrogen-carbon-carbon-hydrogen bond, right? Where it's hydrogen, big circle is a carbon, little dot is a carbon, and hydrogen bond there. And what we're going to do is we're going to take this through a rotation. What I want you to notice is that there are 2 forms here. There's an eclipsed form, which is shown here, and we kind of think of an eclipse where something's in front of something else. It's these 2 guys here. Okay, so everything's eclipsed, and this is staggered where everything is spread out. Okay, what I want you to notice is when we do a rotation, the eclipsed conformation here has a higher energy than the staggered conformation. So let's talk a little bit about why that is. So as I mentioned on the previous slide, we see kind of 3 rotational conformations in this figure where ethane's energy is at a maximum, right? And so ethane's energy is at a maximum at 0, 120, and 240, right here. Boom, boom, boom. Okay? Those are the eclipsed conformations. Right? Because those carbon-hydrogen bonds at the front carbon cover or eclipse those on the rear carbon atom in the Newman projections. Now, because hydrogen substituents are all identical, that's why these 3 conformations are indistinguishable. Notice there are also those 3 rotational conformations of CH3, CH3, in which the energy is at a minimum, right? Here at 60 degrees, 180, and 300 degrees. And in the Newman projection of these conformations, the CH bond on the front carbon is going to bisect a pair of CH bonds on the rear carbon. So the bonds to the front and the rear carbon alternate around the circle, and that's what we call a staggered conformation. Okay, and so when we read from left to right here, we see alternating staggered and eclipse. Now, let's, I love a good question. So why are eclipse conformations higher in energy than staggered conformations? Well, as we can see in this figure, okay, so we're back to looking at the electrons here. the electrons making up the carbon-hydrogen bond on adjacent atoms, right? So these are all carbon-hydrogen bonds, are closer in an eclipsed conformation, resulting in electron repulsions that cause energy to rise. So here we end up with electron repulsions that cause energy to rise, okay? Because of this rise in energy or strain, so we refer to this a lot of times as strain, okay, occurs on a rotation of the single bonds, we call it torsional strain, okay? Also, because the carbon-hydrogen electron groups are closest when the conformations eclipse and are farthest apart when it's staggered, we can also say, right, that eclipsed conformations possess a torsional strain and staggered conformations do not. Okay. So eclipsed has torsional strain, staggered do not. Okay, and so we've got torsional strain because we're twisting. Now, we also have a rotational energy barrier. So ethane molecules aren't locked into the same staggered conformations indefinitely. At room temperature, the staggered conformations constantly interconvert between each other, so they're constantly doing this through rotation around that carbon-carbon single bond, and they easily overcome that rotational energy barrier. So when we talk about a rotational energy barrier between two conformations is the difference in energy between the beginning conformation and the highest energy conformation the molecule must pass through to arrive at the ending conformation. Okay, so just to put this in a little bit different way, to get from one staggered conformation to another requires the molecule to have enough energy to surmount a rotational energy barrier, right? And so that's kind of this hill here. So that rotational energy barrier between two conformations is the difference in energy between the beginning conformation, right, and then the highest energy conformation through which the molecule must pass to arrive at the end conformation. In the case of ethane, this is simply the difference between the staggered and eclipsed conformations, and that's right around 12 kilojoules. Okay, so it's right around 12 kilojoules. Okay, and so we can see kind of where we're getting that 12 kilojoules is right there. Okay, so there's 0 kilojoules, 12 kilojoules, that's what we're looking at. Now, maybe the burning question in your heart is, where does ethane acquire enough energy to overcome the rotational energy barrier? And that answer is thermal energy. Okay, so ethane acquires enough energy to surmount the rotational energy barrier through thermal energy, okay? And that's the average energy available through molecular collisions as the temperature increases, okay? So we see thermal energy here, okay? And that's the average energy available through molecular collisions. So we get that through those molecular collisions. Ooh, let's pretend like I can spell collisions, right? As the temperature increases. Now, the average thermal energy is calculated as the product of RT, where R is that universal gas constant and T is the temperature in Kelvin. And so if T is right around 298 Kelvin, the average thermal energy is right here, right around 2.5 kilojoules. And that's obviously less than the 12 kilojoules per mole rotational energy in ethane. But a fast interconversion from one staggered conformation to another just doesn't require every molecule's energy to exceed the energy barrier simultaneously. So we're right here, right? And what we find is that only about 2% of the molecules possess 12 kilojoules per mole of energy from that thermal energy. But that's enough to make it so that this is we're seeing these rotations as we go, right? So all that's required for a significant percentage of the molecules to exceed that energy at a given time, right? And so as we see from this figure right here, about 2% of the molecules at any given time have sufficient energy. And that's that energy barrier for ethane. But they don't all have to have them at the same time, okay, for this to be going on. Well, I'm sure the burning question in your heart now is, what if we're not looking at ethane? What if these two groups are different? Is there a difference in energy? And the answer to that would be yes. So here we are going to look at bromine. So what we've done is if one hydrogen atom on each of those CH3 groups is replaced by another substituent, and this is what we're showing here with bromine, the energies of the three staggered conformations are no longer the same. So what we find here is the energies, right, of the three staggered conformations are no longer the same, right? So when we look at this, we also see that the energies of the three eclipsed are also not the same, right? So the energies of the eclipsed are also not the same anymore. Okay, so we've got some big differences here. The differences in energy among the staggered conformations and the eclipse conformations are mainly due to a much larger size of the bromine atom relative to the hydrogen atom. Okay, so bromine's going to be a lot bigger. And so as those bromine, I want you to notice that as these bromine are brought closer together through rotation around the carbon-carbon bond, they are going to have a higher energy here. And so that's where that higher energy is. Their electrons, these guys have huge electron clouds, right? And so those electrons are forced to occupy the same space. And electrons have those negative charges, and so they tend to repel each other. And this is a form of strain called steric strain. So the reason that we see higher energy here is because of steric strain. Now, look down here. When these two bromines are just 60 degrees apart, that's called the gauche or gauche relationship here. So they have a gauche relationship. If you paint, that's called gouache. That's not how we generally pronounce it in chemistry, but what you're going to find is people pronounce it a lot of different ways. So this is a gauche conformation. It's staggered. When they're just one away, it can also be just one away this way. When the bromines are on exact opposite ends of each other, this is called the anti-configuration. I want you to notice when these bromines are on the exact opposite end, the farthest apart, this is what has the lowest energy because there's less steric strain. So we can do some averages here and figure this out, and we will work on drawing some of these in class. You of course won't know the definite relative energies here, like what this axis is, but you could say, well, I know because of steric strain, this is going to be the highest energy. I know that this would be the lowest energy, and that the gauche here and here would be the next lowest, and then these two would be the next highest. So you should be able to draw this based on just the idea of steric strain. Now, let's talk a little bit more about those gauche and anti-conformers. What we find here is the as I mentioned, I just want to put some words to it. The anti-conformation, those bulky groups are 180 degrees apart in a Newman projection. And in the gauche, those bulky groups are 60 degrees apart. The gauche and anti-conformations are what we call conformers of each other. Okay, so they're different conformations, so we say those are conformers of each other. And you can see we have different models here. There's the Newman projection. There's what we would consider the side view of a molecular formula, but this is the one that I really like. This is a space filling, and you can see those bromine atoms, their electron clouds, really crashing into each other. So if there was a little bit of a breakup there, I had to pause the screencast and come back. You didn't miss anything. So I just love to reiterate things, and I want to make sure that you really have it in your notes. We've already talked about this, but substituents that are gauche to each other contribute steric strain to the molecule, and substituents that are anti to each other do not. That's why anti is at a lower energy than gauche. All right, maybe the burning question in your heart is, hey, Dr. Pierce, we've been looking at some small molecules. What happens if we get two big molecules? Well, we end up, and what we're going to see, and what you've already seen, is we tend to draw longer molecules in a zigzag conformation. And so for longer molecules like hexane, which you see here, there are several single bonds where we can get rotation, right? And so that gives rise to tons of different conformations. And each of those conformations can exist either as gauche or anti. But what we find is the most stable conformation of hexane is the all anti conformation. So the most stable conformation of hexane is the all anti conformation, and this is also known as the zigzag conformation. And so that's why we draw. So hexane takes this conformation where everything is anti to help reduce some of those steric interactions. And so when we draw something in a zigzag like this, it's because that's the form it tends to take, because each of those bonds is anti. Well, this concludes our kind of introduction to conformers. In the next screencast, we are going to talk about different conformers that you can have with rings, because we don't want to forget those rings. Those are still around. So we're done. Yay!